Hello. In this video we will wonder why there are so many concurrent lines in a triangle. I should say that I am not sure I have an answer to that question. But I think I found something that might be of interest and I'd like to share it with you. So first we're going to review the classical cases, some classical families of lines in a triangle that are concurrent. First, there are the medians. I recall the definition here in case you forgot. And the three medians in a triangle intersect at the center of gravity, also called the centroid. And there are also the angle bisectors, which meet at the incenter, which is the center of the largest circle you can fit into the triangle. And also the altitudes meet at a point which is called the orthocenter. And finally, there are the perpendicular bisectors, which meet at the circumcenter of the triangle. But there are many other lines in a triangle which are concurrent. I won't explain all of these, what are these lines, but let me just quote the Fermat lines, the Napoleon lines, the splitters, the cleavers, and so on. In fact, the mathematician Clark Kimberlin defined a general notion of a center in a triangle. And if the lines you are defining have a geometric meaning, and if they are concurrent, then the intersection point will be a center in the sense of Kimberlin. In his online encyclopedia of triangle centers, there are already 84,000 entries, so there are at least 84,000 centers in a triangle. Not all of these centers are meeting points of lines, but some of them are, and that's already a lot. So that raises the question why there are so many concurrent lines in a triangle, and my aim here is to review some classical proofs and try to find a general principle that could help us prove that lines are concurrent in a triangle and maybe understand why they are. So the first proof is for the medians. There is a very simple proof that you can present to high school students. It goes like this. You take two medians, for instance, the median A prime and B prime, and you call G the intersection point of your medians. And the goal is to prove that G also lies on the third median. To do that, you define another point, which is called D, and is such that GBDC is a parallelogram. Thanks to this parallelogram and Thales intercept theorem, you can prove that G lies on the other median. I let you think about it. If you speak French, and if you like, you can find the proof in my book. I give you the reference here. I will also give links in the description to complete proofs of the theorems I'm explaining right now. Now there is a second proof which is a bit more enlightening, and it goes like this. You define G as the barycenter of A, B, C with equal weights. So you can take, for instance, weight 1 for A, B, and C. So G will be the center of gravity. And the goal is to prove that it lies on each median. And it's quite easy using a general property of the barycenter, which is associativity. So G being the barycenter of A and B and C with weight 1, it is also the barycenter of A and B with weight 2, so the barycenter of A and B each having weight 1 gives you the midpoint of AB, and this midpoint will have a weight which is the sum of the weights of the points A and B. So C prime has weight 2 and C still has weight 1. So G will be the barycenter of C prime with weight 2 and C with weight 1. The fact that it's a barycenter of C and C prime already yields that G lies on the median. But in addition to that, you get a bonus that G lies at 2/3 of this median, because it's the weights are 2 and 1. So it's easy to see that it's C prime G is 1/3 of C prime C, or if you like, CG is 2/3 of C prime. So that's all for the medians of the proofs. Now let's move to the perpendicular bisectors. Here the proof is so easy that I give just one. I can't imagine a simpler one. So you take a point O, which is the intersection point of the perpendicular bisector of AB and BC, and there is a property of perpendicular bisectors. The points on this line are exactly the points which are at equal distance from A and B. So if O is on the perpendicular bisector of AB, then OA equals OB. But since it's also on the perpendicular bisector of BC, you also have the equality OB equals OC. And by simple transitivity of the equality, then this entails that OA equals OC, so that O lies on the third perpendicular bisector. Quite simple. It's a little bit more tricky for the angle bisectors. So here the strategy is the same. You consider I, which is the intersection point of two angle bisectors, and you aim at proving that it's also on the third bisector. To do that, you can use the angle bisector theorem. This theorem says that the angle bisectors divide the opposite side. Let's say that we are talking about the angle bisectors from A, and these angle bisectors will meet the opposite side at a point A prime, which divides this side in two segments which are whose ratio is equal to the ratio of the sides. So A prime C over A prime B equals AC over AB. And there is a converse to this theorem. If A prime satisfies this equality, then it lies on the angle bisector. So the idea is to use the direct sense of the theorem for two bisectors and the converse for the third bisector. And it also uses transitivity. I let you finish the proof if you like, and now we turn to another proof which is more similar in spirit to the proof we gave for the perpendicular bisectors. In this second proof, we use another property of the angle bisector, which is that the points on this line, the angle bisector, are exactly the points which are equidistant from the side of the angle. For instance, the point I is at equal distance from the side AB. So if you draw a perpendicular line from I, it will meet AB at some point H, and the distance IH is the minimal distance from I to the side AB. And similarly, if you draw a perpendicular line to AC. So I is at equal distance from the side AB and AC. But then if it also lies on another angle bisector, it will be at equal distance from the other two sides. So it will be at equal distance from all sides of the triangle, and so will also be on the third angle bisector, just by transitivity again. Now let's turn to the altitudes. It's quite surprising that the ancient Greeks did not know that the altitudes are concurrent, either because they did not notice that fact or maybe that they couldn't prove it. The first proofs of that fact go back, I think, to the end of the 17th century. I will just now give you one by Gauss, which is very pretty, and it uses another triangle. So you start from a triangle ABC. C is this point here in the middle, below, which for some reason does not appear. And so you start from ABC and you construct another triangle, which is called the anti-median triangle, and you build it in such a way that A, B, and C are the respective midpoints of the sides of the large triangle A prime, B prime, C prime. How can you do it? Well, it's quite simple. You start, for instance, by the point B, and you draw a line which is parallel to AC, so it's to the side opposite B. And you do the same. For instance, from A, you draw a line which is parallel to the side opposing A, and so on. And it's easy to prove using intercept theorem that the large triangles is such that its midpoints are exactly the vertices of the small triangle you started from. Well, now that you have this large triangle, you draw the perpendicular bisectors of this large triangle. You already know that they meet at some point, so they are concurrent. But now look, the perpendicular bisector through B is, of course, perpendicular to A prime C prime, but since A prime C prime is parallel to AC, it is also perpendicular to AC, and since it goes through B, it is the altitude from B in the small triangle. So the perpendicular bisectors in the large triangle are the altitudes in the small triangle. And that's why they are concurrent. You already know they are, because you know the perpendicular bisectors are concurrent. That's really nice proof. However, it's hardly generalizable to other cases of concurrencies. But still, it's really nice. So now let's turn to another proof, which is maybe not so pretty, but in fact we will see is highly generalizable. It's a vector proof. You observe that this quantity here, this sum of three scalar products, three dot products if you like, is always zero for any point M in the plane. So AM, vector AM dot vector BC plus etc. You do a cyclic permutation and the sum is always zero. You can find this in my book, but it's easy to prove using a Charles relation. Well, once you have observed that, now look at the first quantity. It vanishes exactly when AM is orthogonal to BC, which means that M is on the line which goes through A and is perpendicular to BC, which is exactly the altitude from A. So this quantity vanishes for points M on the altitude from A. Similarly, this quantity vanishes for points lying on the altitude from B, and so on. So if you take a point which is on the intersection of two altitudes, say the altitude from A and the altitude from B, then these two quantities will vanish, and so the third will also vanish because the sum of the three is always 0, and so your point will also have to lie on the third altitude. So now we are looking for some general principle which could apply to the four classical cases. There is a theorem which is well known and is called Cheval theorem, which says that if you take three lines going through the three vertices of your triangle, and if you define the points A prime, B prime, C prime, like I already did before, for instance, A prime is the intersection point of the line going through A and the opposite side, then with this definition, the theorem says that this quantity is equal to -1 exactly when the lines are concurrent. So this can be used to prove that the medians are concurrent. It's really easy. It's a little bit more tricky, but it's possible to use it to prove that the angle bisectors or the altitudes are concurrent. But you can't use this theorem to prove that the perpendicular bisectors are concurrent, because these lines do not go through the vertices. So this is a general principle, but it has a limited scope. It's limited to the lines that go through the vertices, and it can be tricky to use. So let's look for something else. We will take as a hint that the fact that we had already two proofs that were really close to each other, and I will elaborate on that. So I will rewrite the proofs that the angle bisectors and the perpendicular bisectors are concurrent using a new language. And to do that, let me introduce a function. So for each pair of points x, y, distinct points, we define some function j, x, y of m, which takes any point in the plane to a real number. For the angle bisectors, these functions, this family of function, will be the distance from M to the line xy. And for the perpendicular bisectors, these functions, this family of function, will be the distance from M to x. So in that case, it doesn't depend on y, but I still write it x, j, x, y. So now let's look again at the proof that the bisectors, the angle bisectors, are concurrent. So a point lies on the angle bisectors from C if and only if, with this new language, GAC of M is equal to GBC of M. But now, if we have this equality and also GCB of M equals GAB of M, meaning that M lies on the angle bisectors from B, then by transitivity and using the fact that GXY is equal to GYX, we also have GBA of M equals GCA of M, and so M lies on the angle bisectors from A. So here we have used transitivity of the equal sign and the symmetry in xy of this family of function. In the case of the perpendicular bisectors, you can write the exact same thing and it goes through. There is one difference. Since jxy doesn't depend on y, we do not have this symmetry property, but in that case we don't need it. You can easily see for yourself that we don't need symmetry in this case. So this is what I call the difference trick. If we can prove that the line we consider is the line of points which satisfy this kind of relation. So if you can define a certain function, a certain family of function depending on 2 points, and if the lines you are interested in are the set of points at which these functions are equal, then using the symmetry, if you have some symmetry property, and transitivity will give you that the lines are concurrent. Okay, so let's try to apply that to the altitudes. So now what we would like is to generalize the difference trig to the altitudes. Let's start by observing that we have already defined in that case a function, but a function which doesn't depend on 2 points but on 3 points. F ABC of m is vector am dot vector bc. This is the function we used without saying it in the vector proof that the altitudes are concurrent. And now this makes perfect sense, because this function depends on the 3 vertices of the triangle. So maybe this is even a better principle, to use a family of function which depends on the 3 vertices. I will call that the cyclic trig, and I'm going to explain that. We notice that this sum is always 0. This is equivalent to saying that the sum of the function fabc plus etc. with cyclic permutation is 0. This is the 0 function. So if m lies in the 0 set of the first function and of the second function, it will obviously also lies on the 0 set of the last function. This is the proof we gave, but now in the language of functions. I call that the cyclic trig, and it seems to be a principle that has a chance of being more general than the difference trig. At least it works for the altitude, but it also works for the medians. Let's explain that. You can define for any point in the plane what is called the barycenter coordinates. Any point is the barycenter of A, B, and C with some weights x, y, z. These weights are not unique, but if you normalize them by asking that the sum of the weights is equal to 1, then the triple of a number x, y, z becomes unique, and we can call it the normalized barycenter coordinates of M. Now let's define fabc of M equals to x minus y. This coordinate minus this coordinate. Then we first notice that this is 0 exactly when M lies on the median from C, because in this case M will be a barycenter of C with some weight and AAB with equal weight, and it means that it's on the median, as we have already noticed. So that's the first observation. But we also note that the cyclic property here holds just because this sum x minus 1 plus y minus z plus z minus x is 0. So thanks to the cyclic trig, we obtain that these medians are concurrent. Okay, so now we have two principles, the difference trig and the cyclic trig. But in fact, it turns out that they are related. The cyclic trig is a generalization of the difference trig. We can see that for the altitudes. In that case, we define this function. But if we insert m using Charles relation, we see that am.bc is equal to am.cm minus bm.cm. And this is exactly like saying that fabc is the difference between two functions g that we can call gac and gbc, and generally defined by gxym equals xm.ym. And we notice that this is a symmetric function in xy. So by the observation we already made that if gxy is symmetric, then the lines defined by the zero set of this difference will be concurrent. So we can also understand that in a different way here, is that thanks to this symmetry, if we add FABC plus FBCA plus FCAB, we see that it is GAC minus GBC plus cyclic permutation, and this is 0 by using the symmetry. So the cyclic trig is a generalization of the difference trig. But I think it's a strict generalization, because I couldn't make the same, I couldn't define functions g, x, y such that f, a, b, c is also a difference of two functions like this in the case of the medians. So it seems that for the medians we can't do that. So the cyclic trig is strictly more general than the difference trig. So what I would like now is to explore this further in another video, and in the meantime you can have fun trying to apply either the cyclic trig or the more particular difference trig to other cases you know of concurrent lines in triangles, and tell me about it. Tell me if it works, and tell me what you think about it. And I hope you liked that video, and if you did, then consider subscribing. It's completely free of charge, and you'll be informed of any updates and any new videos. Thank you. See you soon.